Okay, in this video we're going to look at the structural properties, the acidity features, and reductions of alkyne groups. Okay, this is a repeat that was in chapter 2, and it was at the beginning of chapter 5 or so also, where we're going to be just looking at some of the essential structural features of the alkyne group. Okay, so alkynes, remember, are compounds that contain a carbon-carbon triple bond. Back in chapter 5, we looked and saw that the bond association energy for the pi bond of an alkene is about 320 kilojoules per mole. But for each pi bond of an alkyne, the bond association energy is comparatively weaker, only about 220. Now there's two of them, but each pi bond itself is comparatively weaker than the pi bond of an alkene. You may be wondering, where do I get these calculations from? Okay, so 375 is what it is in ethylene. Twice 375 would be 750. If we subtract 375 from 720, I guess it's 345, but the sigma bond contribution, because it's between two sp2 orbitals, is a little stronger, so I drop it down to 320, and I do the same for the alkyne, because remember, the higher the percent S character, the stronger the bond is going to be. So I dropped the CC bond energy down a little bit and came up with this number 220. It's not an exact number, it's only an approximate number. Okay, so remember that in an alkyne we have two pi bonds, and the easiest way to illustrate it is through this angle that I'm showing right here. Okay? Alright. Alright, so we have two pi bonds. Remember, the pi bond comes from overlapping p orbitals that are parallel to each other. Okay, let me orient this thing a little better here, sorry. Okay, so there's our pi bond for that, and then we have another pi bond here from these two p orbitals overlapping. So the p orbitals are at 90 degrees bond angles to each other, just because that's the bond angles on the Cartesian axis. Okay, let's look at some of the structural nomenclature and physical properties issues. We're not going to go through that much of these because there's a lot of commonality with alkenes and alkanes here. Okay, so nomenclature, I can summarize the rules for naming an alkyne by saying it's the same rules as alkenes, except that you're going to end the name in Y-N-E. The number is going to be defined by the first alkyne carbon in the chain. We're going to find the longest chain that contains the alkyne, and the second alkyne carbon is going to be considered the number after the number that's defining the alkyne position. So what is the name of this chloroalkyne shown here? Okay, we number from the left end because that puts the alkyne at the 2 position. Numbering at the right end, hypothetically, if this were carbon 1, this carbon here would be 1, 2, 3, 4, 5, 6. We would not get to the alkyne until we got to carbon 6. Okay. So here's the name. 7-chloro-6-methyl-hep-2-ine. In the older nomenclature, you would put 2 before heptine, but this is the way it's supposed to be done now. Okay, I want to illustrate another thing with this molecule. Some of you probably would look at this and say there's only 5 carbons. Okay, so this is a carbon. That's a CH3. this is a carbon, and this is a carbon. Some people think that this is the way that we show an alkyne. It's not correct. If you look at carbons 1 through 4, that's 4 carbons, not 2 carbons. So just get accustomed to seeing this type of picture here. Okay. Physical properties, we don't need to say much. The only significant intermolecular interaction is the van der Waals attractions, and the physical properties that we would see would be the same as for alkenes and alkanes. Okay, let's look at structural issues. All right, so recall that in a linear molecule, like an alkyne, that the CCC bond angle is 180 degrees. This puts a lot of strain in like 6 and 7 membered rings like you see here. These two compounds on the left, they've actually never been isolated before. They've been generated, but they react spontaneously very quickly. And the reason for this is because there's a very high degree of angle strain in these, okay? This wants to be 180 degrees, but a perfect hexagon. Is 120 degrees, right? So this is quite a strained molecule. It's not till we get to the 8-membered ring cyclooctine shown here where we get to a compound that can actually be isolated. Cyclooctine, even though it can be isolated, it's an extremely reactive compound. It only exists in your refrigerator for a couple of days. You have to make it fresh if you want to use it. It's not until we get to a 12-membered ring shown like I've shown here, where the angle strain associated with an alkyne totally disappears. Okay, strained alkynes have been a feature in the design of some relatively novel antibiotics that have recently been discovered. Because these alkynes are so strained, we're just going to take this part of the molecule here. It does an unusual reaction, which is commonly referred to as the Bergman cyclisation. So it's kind of a fancy way that this operates. An enzyme cleaves one of the sulfur-sulfur bonds. It adds to this double bond right here, and this sort of scrunches the ring a little bit, and then it undergoes this Bergman cyclization. And then wherever that happens, this free radical just starts tearing up the DNA of everything in the vicinity. So this is a very novel mode of action for an antibiotic and to some extent an anti-tumor agent. So these were discovered for the first time, I believe, in the 1990s, and they're still experimental, but anytime you can get an antibiotic with a novel structure like this, it's an exciting find because, as we know, organisms have become resistant to a lot of the antibiotics that we're already using. Okay, so here's a problem for you. Again, pause the video and try it yourself, and then restart it and you'll see the answers. Rank the following compounds in terms of their anticipated heat of combustion. We're going to give number 1 to the lowest energy or the most stable molecule. That's the molecule that'll have the lowest heat of combustion. And number 5 to the highest heat of combustion or the least stable molecule. We can make these statements about most and least stable because all of these molecules have the same formula, I believe. Okay, do they? No, one of them. Let's make sure that this one actually has a methyl group. They should all be C9 compounds. Okay. All right. So if we look at these, we'll call these compounds A, B, C, D, and E. The most stable compound is compound D because pi bonds are more stable when they're part of alkenes than when they're part of alkynes. In the next chapter, we'll learn that compound D also has an additional stabilizing influence because of the relative position of the two alkene groups. So D is the most stable compound. We're going to rank this as number 1. And we're going to rank as number 5 compound A because, remember, we said we cannot have an alkyne in a 7-membered ring, but all of the other compounds are capable of some sort of room temperature lifetime. Okay, so here's the basic issues that are going to use in the ranking. And D is number 1. The alkyne that's not in any sort of ring is number 2. The 8-membered ring, the 9-membered ring one would have the least strain of the cyclic alkyne, so we're going to put that as number 3. The 8-membered ring is number 4, and the 7-membered ring is number 5. Okay. All right. Let's look at another unique property of alkynes among the hydrocarbons. Alkynes, another nomenclature issue that's important is this term terminal alkyne versus internal alkyne. An internal alkyne has no hydrogens directly attached to the alkyne. A terminal alkyne does, and if there's a hydrogen there, of course, the chain has to end there, so that's why we call it terminal. Okay, so this hydrogen that's attached to an alkyne is actually a fairly acidic molecule. It has a pKa of about 25. So hypothetically, we should be able to take an alkyne and a suitably strong base and convert it to the corresponding anion. This type of anion is referred to a carbanion, which just means that the anion exists at a carbon atom. We really haven't seen any of those except, I think, in some early predict the structure of the weirdo molecule questions in chapter 1. Okay, all right. So this pK of 25 presents a dilemma. The strongest base ever encountered probably in general chemistry or to date in organic chemistry was the anion of an alcohol or hydroxide ion. But hydroxide ion and sodium ethoxide are both derived from things that have pKs about 16. So if you use those to do this deprotonation reaction, the equilibrium goes the wrong direction. Okay, it goes to the left. Remember, acid-base reactions proceed in the direction of neutrality. And this is our strong acid. And this is our weak acid. So the weak acid is on the neutral side, right? So this is proceeding in the wrong direction. To deprotonate an alkyne, we have to bring in stronger bases than hydroxide. And here are 3 suitable bases: NaNH2, N-butylithium, or LDA. These are extremely strong bases. They're NaNH2, which is the one that you're most commonly going to see depicted in the reaction equations in this chapter, is the conjugate base of ammonia. So ammonia is not a very acidic compound. Its pK is about 33. Butylithium is the conjugate base of butane, and its pK is about 60. And LDA, or lithium diisopropylamide, is the conjugate base of diisopropylamine, which is just an analog of ammonia. All of these compounds have basicities significantly higher than hydroxide ion, which is derived from something with a pKa of only 16. So all of these compounds will react violently with water. So you have to be very careful how you do these reactions with these bases. You can't have any water or alcohols or anything like that around. Otherwise, they'll just become hydroxide ion. All right. So if this terminal alkyne is treated with NaNH2, often the solvent is ammonia, but it can be anything that doesn't have an acidic proton. You get the sodium salt of the acetylide. Sometimes it's pictured this way. This is a bond. It's a covalent bond, but it has a very high degree of ionic character. And in this section here, you should just regard this as being an ionic compound as equal to that. Okay. All right, so what's making acetylides acidic in the first place? It has to do with the lone pair orbital for the carbanion. Okay, so there's our orbital here. Okay. All right. So the anion orbital is basically going to occupy the orbital that the CH bond used to occupy before the deprotonation step. So this anion here is in an sp orbital. When we remove the proton from ethylene, we get the vinyl anion shown here, and this is sp2 orbital for this lone pair here. When we remove the hydrogen from methane, which has a pK of 60, this is the orbital, or the anion orbital is sp3. So this is the least acidic of these compounds. This is by far the most acidic. And this is, of course, the least basic. And this is the most basic. All right. So the reason that terminal alkynes have this unique acidity is because the resulting carbanion lone pair has a very high degree of S character. So the S character here is 50%. This orbital is 50% S. This orbital here is only 33% S. And this orbital here is only 25% S. Okay, so an S orbital spends a lot of time closer to the nucleus, which has a humongous positive charge. So that's stabilizing. It's more stabilizing to have an anion in a high S character orbital. So that accounts for the fact that terminal alkynes are uniquely acidic. Okay, these very high pKa numbers, pKa greater than about maybe 35 or 40, these kind of anions are difficult to make. In a deprotonation reaction. So these are typically made by these metal reduction reactions, which we're going to discuss in chapter 14. So butyl lithium, which is the technically the conjugate base of butane, is never made by deprotonating butane. It's made by taking N-butyl bromide and treating it with excess lithium, and this reduces the carbon-bromine bond to a carbon-lithium bond and generates lithium bromide in the process. Actually, yeah, we don't need that 2 there to balance the equation. Okay, it's balanced without that 2. Okay, we do need the other 2, the 2 in front of lithium metal. Okay. All right, so let's look at these compounds here and see if we can find the most acidic hydrogen in each of these. Okay, and then your task is just to circle it. All right. So again, pause the video, do it, then start it. And the one on the left, the most acidic hydrogen, is the terminal alkyne hydrogen. The only ones, all the other hydrogens are either at sp2 or sp3 carbon, and that can't compete. All right, the next one has an internal alkyne group and an NH2 group. An internal alkyne, since there's no hydrogen directly at the alkyne, is not an acidic compound. Okay, thus that is the most acidic compound, or most acidic hydrogen in this compound. In the next one we have an OH, remember those have pKs of around 16 to 18, and a terminal alkyne which has a pK of around 25. Our most acidic hydrogen is that. I can tell you that a large number of the students are going to circle the alkyne hydrogen because of the humongous emphasis in this chapter on the acidity of that hydrogen. But just remember that it's still not as acidic as a hydrogen at oxygen. All right, in this next one, there really aren't any acidic hydrogens. I don't think this would react with any sort of base. Maybe butyllithium. Actually, it will react with butyllithium because of the neighboring oxygen. That's an issue in a graduate organic synthesis class, but that is our most acidic hydrogen. And the one immediately above it, of course, is equal to it by symmetry. You could have circled either one. All right, the last molecule has a hydrogen at a terminal alkyne, at an OH group, and at a carboxylic acid. Let's go with the one that has the word acid as part of its name. Okay, carboxylic acid have pKs of around 5. They're much more acidic than alcohols or terminal alkynes. All right, what can we do with these acetylide anions? We can perform alkylation reactions. All right, so the alkyne, terminal alkyne, reacts with NaNH2 to generate the anion. Nobody really ever isolates the anion. What they do is they immediately react it with an alkyl halide to generate a more complex alkyne. So this equation usually is represented just by this set of reagents right here. Okay, so let's look at an example of that reaction. Sorry I didn't make R1 a real group, but I did make R2 a real group. So here we see that this primary iodide is reacting successfully with the alkyne. Okay. What looks like I've written, there's an SN2 reaction, and that is in fact correct. That's what that is. And with a secondary iodide over here, E2 prevails due to the fact that this anion here is very basic. Okay, so we can summarize this alkylation step in that it's an SN2 reaction. It should be bromine or iodine or tosylate. Occasionally it's chloride, but not usually. It needs to be a little bit more reactive than that usually. It's never fluoride. R2 should be methyl or primary, because when it's secondary or tertiary, the E2 pathway takes over. And again, this is something we discussed in the previous chapter. When something has a very high degree of basicity, it very often reacts with secondary halides to make alkenes, and almost always reacts with tertiary halides to make alkenes. Okay. In each case, this is a problem here. Again, do it yourself and then restart the video and you'll see the answers. But show two chemical equations for the preparation of each internal alkyne through a terminal alkyne alkylation process and determine which of them is likely to be more successful. All right, so in the terminal alkyne alkylation, remember that we're forming either of these bonds between the acetylide carbon and the alkyl group immediately adjacent to it. Okay, so there are two ways to make this. I can make bond A or bond B. All right, so if I make bond B, I'm I'm going to have to start out with a cyclohexyl acetylide, deprotonate it, and treat it with methyl iodide. If I want to make bond C, I'm going to have to start with the methyl acetylene, or propyne, and deprotonate, and then treat it with a cyclohexyl halide. Okay? The one at the top is going to be better. Elimination is going to win out over substitution in the bottom case. This is not going to produce this. It's just going to do an E2, and we're going to get those two compounds. All right, let's do the second one. And again, it's not bond C, that's bond A. Sorry. We can make either bond A or bond B. Okay, making bond B. Involves treating the, the acetylide that already has an isobutyl group and putting on the propyl group. If we want to make bond A, we start with 1-pentyne and then deprotonate and treat it with isobutyl iodide. Okay, so as far as to which of these is better, you just look at the quality of the SN2 reaction. This is a primary halide. And this is also a primary halide, but it has a substituent at the beta position. So we're going to choose the top one as being better because the SN2 part of this reaction is better with a simple primary halide over the primary halide that has the beta substitution. Both of them will probably work to a large extent, but the one at the top is going to be a little bit more easier, though a little bit easier. Okay, the skill set, it'll be a little bit more forgiving of like an unskilled chemist, whereas the one at the bottom would require a real professional probably. Okay, that's probably not the way to best way to say it, but the one at the top is going to have a higher substitution to elimination ratio. Okay, let's look at the synthesis of alkynes. The most important synthesis route is the alkylation reaction in the previous slide. Okay, so the most important synthesis of alkynes is from simpler alkynes. Another important route is via the double elimination from 1,1 and 1,2 dihaloalkenes. Okay, so if we treat a 1,2 dihalide, like here, with 2 moles of a very strong base, very often it's NaNH2, sometimes it's potassium tertiary butoxide, it's usually just a very strong base. The E2 occurs twice to make the acetylene. Okay, you can also use a 1,1 dihalide like you see here. This is less useful because what we're going to see is that the only reaction in 313 or 314 that we ever cover that makes a 1,1 dihalide uses an alkyne as its starting material. Okay, so as far as like that's not going to have any net utility. We turn it into something, then turn it back into what we started with. That's kind of a generating chemical waste for no reason. Okay, so here's what's happening in this reaction. Our first mole of base is doing an E2 reaction to make a vinyl halide. Okay, that's what we call this type of intermediate, a vinylic or a vinyl halide. And our second mole of base is doing another E2, as you see here. It is possible to stop the reaction at this stage right here and isolate this compound if you really wanted to. It's mostly, you get this as an easy mixture, and the acetylide is generated in the second step from both the E and the Z isomer. Okay, it doesn't have quite the rigid anti-periplanar requirements because no matter whether it's E or Z, the hydrogen CH bond is perfectly overlapped with the halogen, carbon halogen bond. Okay? All right. Okay. So, anyway, it is possible to stop the reaction right there. This reaction is really often not that clean. It's typically used when there's no other competing process available. All right, let's say, how would you accomplish this transformation right here? Alkene to alkyne. This is a very common one that you see. All right, so what you do is you take advantage of the fact that way back in chapter 6 you learned a reaction that makes that type of compound. Okay, so this is typically done by adding halogen to the alkane and then doing this double elimination right here. Okay, I'm going to pause the video or stop the video right here because the remaining video is going to deal with the reactions of alkynes. Okay.